What's the music?
Today, we're going to continue talking about some special probability distributions. So last time, on our first class, we talked about the idea of a probability distribution in general, right? And we noticed that, hey, to compute some of these probability distributions is like really a kind of a pain in the neck. You know, and we observed that, hey, like this one particular type of probability distribution, if my random variable is describing that type of situation, I can compute these probabilities with a formula, right? We call that a binomial distribution. Today, we're going to talk about another special type of probability distribution, this time for a continuous random variable as opposed to a discrete random variable. Who remembers the difference between continuous and discrete as a starting point? Yeah, go ahead, Nicole.
Continuous can be in the domain, it could be 1 or 2, so then if it's discrete 1.
Kind of.
Continuous can be like numbers between like 1 and 2.
Yeah.
Okay.
2.
Right, so continuous means that it's going to cover like some interval of the real line, right? Like all the decimals between 1 and 2 is a continuous piece, as opposed to like 1 and then 2, which is discrete, or even like all the rational numbers between 1 and 2, even though there's infinitely many of them, that's still discrete because none of those rational numbers are directly next to each other. There's always like some irrational numbers between them. Is everybody okay with that? So if our continuous random variable can take all the values, say, between 0 and 1, how many different x values are going to be in our probability distribution? So our random variable is continuous. You can take all the values from 0 to 1. How many x values are going to be in our probability distribution? More than 1. Infinitely many, right? So for a continuous random variable, are we ever going to write out a probability distribution like we've done before? If I try to graph this, am I going to get a histogram? No, what I'm going to get is like a curve, right? Is everybody okay with that? So I just want to like differentiate what we're doing here right at the start and talk about like some of the difference between a situation with a discrete random variable versus a continuous random variable, and some things that make sense to do in one case and some things that make no sense to do in another. What's nice about a continuous random variable is that the probability that, say, x is less than or equal to 1 is the same as the probability that x is less than 1. We'll talk about why later on. Is that the same in for a discrete random variable? No. Big difference between those two. It's okay? We'll talk more on that in a moment. Eventually, at least. All right, so we want to start out by talking about something called a density curve, not physics density. So a density curve satisfies the following two conditions. It's always on or above the horizontal axis, like the x-axis. And the total area under that density curve is always equal to 1. So if the total area under the density curve is equal to 1, that makes it an ideal candidate to describe a probability distribution, because the sum of all the probabilities in our probability distribution has to equal 1. So for example, if I take this discrete random variable that describes the scores of 7th graders in Gary, Indiana on the Iowa test of basic skills. You see the histogram that's built there? I could fit a density curve on top of that histogram so that the total area underneath that density curve is still 1. So all those probabilities still add up to be 1. And I could use that to like model this data to approximate what's going on, what I observed in my sample of these Gary, Indiana test scores. Is everybody okay with that idea? Okay. So on your density curve, we're going to want to be talking about where things are like the mean and the median and the standard deviation, all these like descriptive statistics that we've talked about during the course of the year. So let's start here with the mean and median. Okay. The median on my density curve is the exact center that divides the curve into like 2 equal halves, right? So it'll be, if the curve is symmetric, it divides it straight in half. If the curve is skewed one way or the other, we're going to find the place where it divides the area. So half of the area is on one side of it, and the other half of the area is on the other side of it. Is everybody okay with that idea? Which makes sense because the median is also the 50th percentile, which means like 50% of the data is above the median and 50% is below it. Does that ring a bell from first semester? Again, trying to connect some of these concepts now together and tie this into a nice, neat bow. The mean of our density curve is going to be like the balance point. So imagine if our curve was made out of like solid wood and I'm trying to balance it on a point. Like where the mean is would be the spot where you could balance it, balance the curve on it. Does that make sense to you guys? Okay. If the curve is symmetric, remember what symmetric looks like? It's like a mirror image of itself, left and right. If the curve is symmetric, the mean and median occur at the exact same point. If the curve is skewed, the mean will be pulled in the direction of the skew, which should make sense, right? If you have, you have 4 test scores, no, let's say 5 test scores, right? Or let's say you have 4 test scores. You have, 4 90s, right? Everybody's okay? 4 test scores, they're all 90. Your median is 90, your mean is 90, correct? Let's say the next test you get a 10. Rough day. What's going to happen to your average? Drops a lot, right? What happens to the median? The middle number is still 90, right? So like there you see why the mean is pulled in the direction of the skew or the outlier. It's a real world example. So picturing this, the curve on the left is a symmetric distribution. The mean and the median occur at the exact same place, the place that divides the curve into 2 equal halves. On the right, we have a skewed distribution. Notice the median should be a situation where the area here on this side of the median is the same as the area there on that side of the median. Everybody's okay? Now it's hard to know that exactly. We're just kind of using our eyeballs to guesstimate it. But the mean will be pulled in the direction of the skew. So in whatever direction that tail is, the mean will be pulled in that direction from where the median is. Be shifted. How much does it shift? Can't say from what we've done so far. Just know that it's moved in that direction. Everybody okay? So just to kind of summarize, our density curve is like a description of the probability distribution. Okay? It's like an idealized version if you have a discrete distribution. But if you have a continuous distribution, it'll just be the same. So if you're using a density curve as an approximation, the mean and standard deviation from the density curve may differ from the mean and standard deviation that you compute from your raw data. That's okay. And again, we use our kind of usual notations. So the mean for our density curve, we use the Greek letter mu, which is kind of looks like a cursive U, but it's actually supposed to look like the letter M. That's what that letter is actually supposed to look like. But and the standard deviation, we use that same lowercase Greek letter sigma. I know, everybody's excited because I said that word. Okay. So one particular type of continuous distribution that we're going to focus on is going to be called the normal distribution. So much like when we talked about discrete distributions, we studied the particular discrete distribution, the binomial distribution. When we talk about continuous distributions, we're going to talk about the particular continuous distribution called the normal distribution. And ideally, we're going to want to do something similar to what we did with the binomial distribution and cook up a way to calculate probabilities for random variables that could be modeled with a normal distribution in an efficient manner. Everybody's okay? So mirroring, another hard word to say. What we did last time, just with a continuous random variable instead of a discrete one. So these normal curves, the density curve for a normal distribution, they're all symmetric. Okay? They all have just one single peak. And they all have a shape that we call a bell shape that kind of looks like a ghost. Right? You put the little zigzag at the bottom, it looks like a ghost, right? All right. We can describe any particular normal curve or normal distribution with two numbers, the mean and the standard deviation. Everybody's okay with that? Or in some cases, you could get the variance instead of the standard deviation, because what is the relationship between the two? Between variance and standard deviation? The square root, right? Yes, the standard deviation is the square root of the variance. So again, if I gave mean and variance, it's okay, that's good enough, right? That'll do. All right. So to formalize this, let's give ourselves a definition now. We say a normal distribution is described by a normal density curve. Any particular normal distribution is completely specified by two numbers, its mean and its standard deviation. The mean of the normal distribution is the center of the symmetric normal curve. The standard deviation is the distance from the center to the change of curvature points on either side. And we abbreviate the normal distribution with mean, mu, and standard deviation sigma as x, squiggle, n, parenthesis, mu, comma, sigma squared. Because what is sigma squared? If sigma is the variance, sigma squared or if sigma is the standard deviation, sigma squared then is the variance, right? Now typically you'd be given standard deviation of the problem, but if they gave you variance instead, it's like, that's fine, right? 6 of one, half dozen of the other. I can do a square root, like not a big deal. So normal distributions are good for some distributions of real data. So most or many things in real life you measure are continuous data, right? If you want to time how long it takes something, or how big something can get, or, you know, like how much something weighs, these are all things that like have continuous data, and a normal distribution might be a good choice in terms of modeling that distribution. Now there's a bunch of other like high-end theorem stuff that work out to be like, hey, even if it's kind of like an unknown distribution, like if I take enough samples from it, it's going to turn out to like approximate a normal distribution. That's like a high-end statistics theorem that you'll see if you take a real statistics course at some point. What's that called? Like the central limit theorem, I think is what that's called. Is that right, Lucas? You remember that?
Yes.
Yeah. So remember in first semester how we did these all those hypothesis tests, like the t-test and the chi-squared test and stuff? You can do other hypothesis testing with normal distributions as well, depending on like what the situation looks like or how much data you have. So you can do similar things with a normal distribution as well. It's a really important one if you take a statistics class, or you're interested in a career where statistics are going to be like kind of a part of your everyday life. Like if you're doing any kind of like social science research, like medical research or psychology research, like statistics are going to be part of your everyday, and you're going to have to get good at, you'll see more of this stuff, you'll get good at this stuff because it's part of your job. You have to. Or even if you're like interested in aspects of finance, like a lot of risk management, you're using like statistical modeling to build out like how exposed you are in terms of this, you know, this investment that you've made, how much cash on reserve should you have to cover this if it fails, what's the probability it fails, what's the expected value for it. So just, you know, anyways. Normal distributions are good approximators of the results of many kinds of chance outcomes. That's kind of what I hinted at with the central limit theorem. And many statistical inference procedures are based on normal distribution. That's what I was kind of talking about with the hypothesis testing. You can do that same kind of hypothesis testing that we did with t-test and chi-squared test with normal distributions. All that kind of stuff is beyond the scope of what we're going to do in this class. But just giving you some picture. So first thing, for a normal distribution, we have the 68, 95, 99 rule, which says that starting at the mean, one standard deviation to the left or right, if I look at this area, that's 68% of the area under the curve. If I look from in between two standard deviations from the mean, that's going to be 95% of the area. If I look at 3 standard deviations from the mean, that's 99% of the area under the curve. Kevin.
So this is for like all the curves?
For every normal distribution curve. Every single one of them. Yes. But only for normals, right? If this was a, you know, t curve or a chi-squared curve or something like no. So again, like 68% of the data is in between 1 standard deviation above and below, 95% between 2 standard deviations, and 99.7 within 3 standard deviations. Okay? So it gives you a nice approximator if you want to calculate the probability that something happens and you don't have a calculator. If the probability, you know, like you can, yeah, it's pretty close to 1 standard deviation below, so we want like, well, you know, you can do some of that. So to give you an idea of how like the mean and standard deviation affect the shape of our normal distribution, let's look at a couple of examples. So note, what do you notice is the same in each one of these three normal distributions that we've listed? The standard deviation. What's different in each one? The mean. So let's take a look. So this is the normal curve for each one of these three normal distributions. What do you notice is different about them? They've just been changed to different locations. The shape of each of these curves is identical. The location of the curve has just been shifted to match where the mean is, right? Because this one, the center should be at 5, the center should be at 10, the center should be at 15, but the shape of the curve is identical, right? So mean controls the location, standard deviation controls the shape. Everybody good? So the bigger the mean, the further to the right it'll shift, the smaller the mean, the further to the left it'll shift. Let's look at how standard deviation affects the shape then. Yes? So let's take a look here. What do you notice is the same for each one of these three normal distributions? The mean. What's different? The standard deviation. Let's look at how the standard deviation changing affects the graph. So notice that all three of these graphs have the exact same center. They're all centered at 5. And what's happening as the standard deviation increases? No. It spreads out, right? So the tallest curve had the smallest standard deviation. The shortest curve had the biggest standard deviation. But the shortest was also the widest, because the area under that curve has to be fixed at 1. So if it's very tall, it's going to be very narrow, because the area is still, you only have 1 unit of area to build. If it's very wide, or if it's very short, it's going to be very wide, because you still have to fit 1 area under that curve. Does everybody feel okay on that? Okay. Okay. How can I use this normal distribution? How is this related to probability and binomial distributions? So let's say that we had asked a group of students to pick any number between -10 and +10. Suppose after we looked at the data, that choice of number was a normal distribution centered at 0. The graph of that is shown below. Notice that I didn't bother including a standard deviation because it doesn't really matter for what I'm about to illustrate. Let's say we want to find the probability that some random student selected a number less than 5. That is P of x less than 5. I could find the area under the curve starting at 5 and going all the way to the left. Right? Now, doing that mathematics to do that is not trivial. It involves calculus, quite difficult calculus, in fact, like beyond the scope of, like your first, maybe by the end of your second year calculus course, you'd be ready to kind of attempt that sort of computation, but even there, it's going to be rather difficult. Now, we still want to be able to calculate that area. So what are we going to use? You're going to use your calculator to do the calculus. Now, when I was a student in high school, we did not have graphing calculators with these statistical distributions programmed into them. You know what we had to use? We had a table. A table in the back of the textbook that you had to look up the values off of and then manipulate the values from the table to figure it out. Just like we had to do the same thing for logarithms. Like if I wanted to do log base 2 of 3, did not have a calculator that would do that. you have to use the change base formula to write them as natural logarithms and then look up the values of the natural logarithms out of the table in the back of the book. In the age of pencil and paper, where like most math courses were no calculator anyway, or very limited use of calculators. All right, so one thing to think about here, since we're talking about a continuous distribution, for any specific value such as x equals 5, the probability is 0. Why would that be? No. So think about graphically what we're doing when we calculate the probability with this continuous distribution. We're looking to find the area under the curve, right? What's the area under a single point? How wide is a point? What's the width of a point?
There's no width.
It has no width, so its width is 0. So if I build like a rectangle to go underneath it, that rectangle has width 0, correct? What's the area of such a rectangle? 0. So if the probability is just the area under the curve, the area under a point is 0, so the probability that x is equal to exactly 5 is 0. Note this is decidedly different than a binomial distribution and all discrete distributions, where the probability of having exactly, x taking exactly one value is definitely not, well, most of the time, not 0, right? It can definitely be non-zero. So because of that, in a normal distribution, and furthermore, any continuous distribution, the probability that x is less than 5 and x is less than or equal to 5 is the same thing. In a binomial distribution, are those the same thing? No. In any discrete, well, in a discrete distribution, are those going to be the same thing? No. Not usually. I mean, it's possible they could be, but like, no, Mr. Kulik, not usually. In a continuous distribution, will those be the same thing? Yes. Specifically, the normal distribution. Okay, I'm trying real hard to emphasize the difference between what you can do with a binomial and what you can do with a normal. Everybody's okay? So, because of that, all four of these probabilities are the same if you're talking about a normal distribution, because less than or equal to, there's no difference in them. So if you're looking for all the stuff between -2 and 5 and it doesn't include those two numbers, or if it includes one of them but not the other, or it includes both of them, all the same probability. In a normal distribution, and more generally in any continuous distribution, but not the same in a binomial or any discrete distribution. Everybody's okay? Let's keep on rocking. So, remember when we talked about percentile rank back in first semester? Right, what was our example of a thing that you guys would have seen that gives you scores as percentiles? Well, your PSAT, right, for sure gives you a percentile score. The ACT gives you that raw number score. I think they probably give you percentiles with it and let you know like where your score fell percentile-wise. But most people, when you ask them their ACT score, are going to say like 26 or 31 or whatever they got, right? You ask somebody their PSAT score, and all they give you is the percentile, because that's all the PSAT reports to you, is like your percentile rank.
It also says.
Does it also give you a number? Okay. Yes. Okay. It's been a while since I've looked at that. No, excuse me for that. So we've talked about this, right? So remember that the percentile P is the the fifth percentile is the value where 5% of the data is below it, right? Can you ever have a 100th percentile? By definition, no, because the top value, everything below it, is not going to be 100% because it doesn't include the very tippy top value, right? So it's always the amount of stuff below it is the percentile. Everybody's okay? So just to review, let's say Jenny earned an 86 on her test. Notice the 86 there is bolded. What is this graph that we're given here that contains the data? What kind of graph is that called? Who remembers the name of this thing? It's a stem and leaf plot is what this is. Should remember those names because on the AP or the IB exam, they'll ask you to be like, make a stem and leaf plot for this data. Like they expect you to remember what that looks like and be able to do that kind of thing, right? Just like we expect at one point for you guys to know how to do that. So the names matter. So I'm just going to kind of keep on reviewing those things as they come up and reminding you that like I made you learn this for a reason because someone else is going to expect you to be able to do this also. So it asks, how did she perform relative to the rest of her class? A percentile rank seems like an obvious choice here. So if we count up, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 scores below her, 21, 22, 23, 24. Total students, I feel like I miscounted somebody. Yep, so I should be 21 out of 25. Sorry. It's hard when you don't get to, like, you can't really, like, touch it. You know what I mean? So she would be 21 out of 25 or the 84th percentile. So everybody feel good on what we did there? Remember doing this first semester? Again, relatively easy to do. Okay. So there is one type of special normal distribution that we want to concern ourselves with called the standard normal distribution. To convert a value from a normal distribution to a standard normal distribution, what we're going to do is we're going to do a transformation called a z-score. So the calculation for a z-score is observation minus mean divided by standard deviation. This is an important concept because it allows you to compare between things that are normally distributed but maybe are under different circumstances, right? So like, say that you're in a class with two different teachers. What's a class that two different people teach? Who's in a class where there's two different teachers? Perfect. AP Lit has Miss Glick and Miss Archer. Great. So who's the harder of the two? Miss Archer's reputation, she's the harder of the two. Perfect. So, you know, like you and your friend, one friend is in Miss Archer's class, the other friend is in Miss Glick's class. You compare your scores on the most recent test, and the Glick person's like, I got an 88. And the Archer person's says, I got an 82. But who really did better? Right? Maybe the 82 was the top score in Miss Archer's class, and the 88 was like one of the bottom scores in Miss Glick's class, right? We need to have a means of comparing them relative to the conditions that they took the test. A z-score is what you'd use to do that. So you'd look at relative to the rest of your peers, how did you really do? What is your z-score? And compare that to the other person and the conditions they took their test under, and you get an idea of what you're representing. What this z-score is really talking about is how many standard deviations your score is away from the mean. So let's say our Archer person's score was like 1.5, their z-score was 1.5, meaning that 82 was 1.5 time or 1.5 standard deviations away from the class average. Pretty good score. And the Glick's 88 person had a z-score of like negative 0.25, meaning they performed a little worse than class average. Who really did better on their test? Well, the person with the 1.5 z-score, right? Does everybody feel okay? This is a natural way to compare things. So if you're talking about like baseball players across eras, how you compare somebody that played in the 40s and 50s with somebody playing now, where the league batting averages and league ERAs and league number of home runs and stuff is vastly different, right? It's almost a completely different game. You want to compare them relative to their own era, and you use like a z-score as a natural way to compare them across eras. You could do the same thing for like quarterback performances or running back performances. It's a natural way to compare sporting outcomes across eras, especially when the game is played very differently over time. Does that make sense? And you could look at, like business performance across eras or across different countries, right? Or even like movie ticket sales, right? Like the highest box office movies of all time are always just like, what's the most recent big hit because of inflation? If you compare it relative to its era, though, anyway, getting on going. So old Jenny here with her 86, the class average was 80 and the standard deviation was 607, so her z-score would have been 0.99, which is a pretty good z-score. You're one full standard deviation above the mean. That's a fairly rare outcome. So what differs a standard normal distribution from just a plain old normal distribution? In a standard normal distribution, the mean and standard deviation are fixed and they are specific values. There is just one mean for a standard normal distribution. That mean is 0. There is one standard deviation for a standard normal deviation. That standard deviation is 1. You talk about a normal distribution, its mean could be anything, and its standard deviation could be anything. Right? There's infinitely many normal distributions because your mean and standard deviation could be any number. There is one standard normal distribution. It is a normal distribution with mean 0 and standard deviation 1. So the nice part is I can translate any normal distribution to a standard normal distribution by taking any observation from my normal distribution and converting it to a z-score. That'll give you the equivalent observation in the standard normal distribution. Again, when I was a student in high school and I did this, the table in the back of the textbook was a standard normal table of probabilities. Every problem, you converted your observation to a z-score, used the table in the back of the book to look up the probability for that z-score, and then did whatever you needed to do after that. But that's like how it worked. The only table they gave you was the standard normal table. And everything was, you had to do a z-score conversion for everything to look at. You don't have to do that because technology is advanced in a way to remove having to look it up in a table has been replaced with just tell your calculator what you're trying to do and it'll give you the number for you. It's not appreciably different other than like it's more convenient. Okay. So I've hinted at that these probabilities calculations for these continuous random variables are related to the area under the curve. We talked about to calculate the area under the curve for like a normal distribution requires a fairly high level of calculus that we do not have and we are not going to have. The calculator is going to substitute for that calculus proficiency. So let's talk about now how to do that. So the first thing you want to do is you need to write down the normal distribution you're working with and write down the probability that you are trying to discover. So like, this is a normal distribution, 5, 2 squared, right? With mean 5 and standard deviation 2. And I'm looking for the probability that x is, less than or equal to 2, or x is between 5 and 7, or I have to write down the probability statement that I'm going to solve. That's my first step, is I need to know the type of distribution I'm working with, and then the probability statement I'm trying to solve. Everybody's good? I figured that was going to happen at some point. Next, I want to perform my calculation. I'm asking you to show your work. So part of that is going to be writing down what you did on your calculator. Write down like normal CDF, and then list the inputs that are going to be there. I would suggest to do the same thing with your binomial stuff. Just write down on your paper what you typed into your calculator. That will help me assess partial credit on things. And then we want to answer the question. So let's look at an example. So given that z is normal 0, 1, find the following probabilities. What type of normal distribution is 0, 1? That has a special name. That is the standard normal distribution. Okay? I promise you on the IB exam, they would not write it as N01. They would just say in a standard normal distribution and expect you to remember that that means the mean is 0 and the standard deviation is 1. That is something you need to remember. Okay? So we're looking to find the probability that -2 is less than z is less than 1. So we have our distribution. We have the probability statement we're trying to find. It's time to go to the calculator. Okay, sketch the curve first. Fine. That's what the curve looks like. Everybody's okay? How did I know where things were going to go? Right, so 0 and 1 was given to you. 0 is the center, and then 1 is telling you the scale for the x-axis, right? Everybody's okay? Now, for this particular problem, I don't even really need a calculator to do this. How would I do this with no calculator? I can do it. I can use the 68, 95, 97, or 99 rule to do this. I know from here to here is 68% or 0.68. Here to here is 95%. So I can do 95 minus 68 to get just those two sections, and then divide that by 2 and add the 68 back in. And I can do this with no calculator at all. Just pointing it out to you. Now, you're allowed a calculator throughout, so you don't need to do it that way. But if this was like A and B, or 0 and B or something, where they don't give you the value, now they're testing you to see if you remember that 68, 95, 95. Everything's okay? So if they hide the standard deviation there from you, so now you can't use a calculator to do it. So I'm going to go to second. I'm going to press the bars button just like before. I'm going to find the normal CDF. that's down towards the bottom. Normal CDF.
Is it number 2?
Okay, is it number 2?
Yeah, the binomials are like the A.
Oh, the binomials were the ones at the bottom. My bad. Okay, it's going to bring up a menu. My lower is the bottom of my probability. The upper is the top of my probability. And then the mu is mean. And the sigma is the standard deviation, which is 1. And then I hit paste.
Yeah.
I hit that. So far, so good. Okay. Let's say I want to do P of Z less than 1. Again, I'll sketch a little picture. I remind you, again, this is something I could do with no calculator if I really wanted to, using the 68, 95, 99 rule. But we are allowed a calculator throughout, and this can be done with a calculator also, so I would suggest using it to do this.
Yeah.
So again, I'm going to do normal CDF. What am I going to choose for my lower? Right? There's no lower value given. What is the smallest value we're going to? Oh, past that. Negative infinity, yeah. How do I type negative infinity into my calculator? I use the smallest number that my calculator will hold, which is negative 1 times 10 to the 99th. You know how to get that capital E that's like second and then like number 7 or something? Is that the scientific notation shortcut on your calculator? You guys know that, right? Mm-hmm. And then when you hit paste and boop, there you go. So picked up a couple of percentiles instead of going all the way to negative infinity instead of stopping at negative 2. Yes?
So if your mean was like 3, then your upper lower bound would be like 0 and 6. Because your graph has to be like in the middle.
If you're no, the upper and lower are just, they come from this.
Okay.
Always. Has nothing to do with the mean and the standard deviation.
Okay.
The mean and standard deviation depend on that. This is going to answer your mean and standard deviation. Upper and lower is always going to come from the probability statement. The two don't depend on each
I
other.
don't know when you're setting your graph.
Oh, when you're drawing your graph?
Yeah.
The labels, yes.
Okay.
So if it was like, 5 comma 2 squared,
Mm-hmm.
it'd be 5, 7, 9, 11,
Right.
3, 1, negative 1.
Yeah.
Yes. That's what you're asking?
Yeah.
Okay. So again, the mean tells you the center, and the standard deviation tells you the scale on the x-axis. Yep. What you're counting by. Okay. Let's do z is greater than negative 1.5. No longer could I do this with no calculator, I want to point out, since it's not ending at one of the standard deviations. Try it on your own. Punch in that calculator. Get it, guys. Get it. You gotta eat. What's the lower? Nope. Negative 1.5. What's the upper? Positive infinity. Which is positive 1 E99.
Okay. That's going to be a CDF though.
Nope, oh yes, always CDF.
Yeah.
Yeah, you never do a PDF for a continuous. So what do we get there? So far so good? Okay. I've done it already with no calculator. It's not 1. It's not 0. It's 0.5.
Oh,
Because remember, how much is the total area under the curve?
1.
1. What is the mean? 0. What does the mean do to the curve? Splits it in half equally. Everything less than the mean is half of the curve, which is 0.5.
There, makes sense.
Right? Like, I didn't need my calculator to do that one, guys. Everybody's okay? Could you type this in your calculator? Yeah, is it going to give you exactly 0.5? I don't think so. Probably give you like 49999. The reasoning is that you're not going all the way to negative infinity. You're still using a number there, just a very, very, very small number. How about this? What do those bars around Z mean? Absolute value. So the absolute value of Z has to be greater than 0.8. What is that? What are some potential values that Z could have? Give me an example of a value for Z that's, when I take the absolute value of it, it's greater than 0.8. Just give me one. Any value. This is like a middle school math question. And you're sitting here like smiling at me, you're like, I don't know.
1.
1, correct. Because the absolute value of 1 is 1, and 1 is greater than 0.8. Can you give me a negative number where the absolute value of it is still greater than 0.8? What would that negative number be? Negative 1. Okay? If I wanted to keep counting, would I need to get the number is going to get further away from 0.8 or closer to 0.8? Further away, right? So my first step is going to be to rewrite this without the absolute value. So I have two sets of numbers, right? I have the numbers that are greater than 0.8. Those will work. And the numbers that are less than negative 0.8. So you see how I sketched that on my picture? All the stuff greater than 0.8, all the stuff less than 0.8. So far, so good? Okay. So what I'm going to do is I'm going to use a complement rule to do this by taking 1 minus the stuff in the middle. Alternatively, what could you have done instead of doing a complement here? You could have calculated this probability plus this probability. Or even, you could have gotten away with one probability computation, because what does it look like those two areas are? Equal, right? So I could just calculate one of them and multiply by 2. Why do I know they're equal? The curve is symmetric. 100%. Very good. So far, so good? All right. So in summary, we state the distribution, write the probability statement. draw the curve if we need to. Sometimes that can be helpful and informative to give you a visualization of like what kind of number should I be getting. Is this going to be a number that's close to 1 or close to 0, somewhere in between? If I draw and shade a picture, that enormously helps, like as a little bit of a safety check. Perform the calculations showing your work. So again, when I say show your work, just like write down what you're typing into the calculator. And then write down your answer. And again, this will go for any normal distribution, not just standard normal distributions. You might have to update your mean and standard deviation depending on the question, but all right, let's do one where it's not a standard normal distribution. Try this one on your calculator. How do I know it's not a standard normal distribution? Good. The mean is not 0 and the standard deviation is not 1. So you could standardize the 9.1 and 10.3 using a z-score and then use the standard normal distribution as before, but you don't need to do that. So you could do this way, but you don't need to. You know, just sketch myself a little picture. Brooklyn, how to get those numbers on the x-axis?
Because you had your 10 and you just counted that deviation.
Which is,
That's your 2 squared.
well, the standard deviation is 2 because it's sigma squared is the input there. So you're counting just by 2's on the x-axis. Yep, starting at the center, which is 10. Okay, plug her in. Notice here that when I type in my, should be sigma. My sigma is 2, not 2 squared, right? When you write the normal distribution, it's always sigma squared there. When you put in the calculator, it just wants the sigma. Oh, I have to square root something. Oh no. You gotta be careful though. It's easy mistake to make. So your final answer should have been 0.233. See people shaking their head. That's good. We got it. Okay. Eggs laid by a chicken are known to have mass normally distributed with a mean of 55 grams and a standard deviation of 2.5 grams. What is the probability that an egg weighs more than 59 grams? I should start by writing my normal distribution. What would the normal distribution be here? The mean is, and the standard deviation is? So I'd say n55 comma 2.5 squared, right? Okay, and what probability am I looking to find? Right, so can we do it with an inequality? Let's say x is our random variable. Okay, so the p of x
Is greater than 50.
Great. So we do that first. So we're looking for this area then, right? Is everybody okay with how the numbers got on the x-axis there? Let's calculate time at this point. And out she spits. It's a big egg. Right, you're almost 3 standard deviations above the mean. Oh, I'm sorry, almost 2 standard deviations above the mean. It's a whopper. It's one of those that barely fits in the little egg carton. How about the egg is smaller than 53 grams? Notice the mean and standard deviation have stayed the same here, right? That's nice. So again, sketch our curve. We're looking for this part. So negative infinity up to 53. Not nearly as rare as that Whopper egg we saw in the first example, right? Here I expect to find, in my dozen eggs, find a couple of little guys in there, right? How about an egg is between 52 and 54? Everybody feel okay there? Again, once you've gotten the hang of this, it's not too bad. What if I want to go backwards, though? What if I want to recover the observation from a percentile, right? So what if I want to go backwards? Like I want to know what value is like, 30% of the data below, or 30% of the data above, or whatever, right? But if I want to go that route. So again, you want to state the distribution. So you're going to write down what kind of normal distribution you have and the values of interest. So you say, P of x less than little x is equal to 0.3 or something, right? And then you're going to perform your calculation. To do this calculation, to go backwards, you're going to be using the inverse norm command on your calculator. And your inputs for inverse norm is your cumulative proportion, your percentile rank. Has to be a percentile. It can't be percent above. It has to be percent below. If you are given percent above, you just have to, flip it, right? Subtract 1 from it to get the percent below. It's okay. And then the mean and standard deviation. Let's do an example. So again, we're told that we have a standard normal distribution, and we want to find the value of A such that the probability Z is less than A is 0.877. So I don't know, I'm just kind of like guesstimating what 87% of the curve looks like. Not really that important. But it gives me an idea that the value should probably be bigger than 1, right? Into my calculator I go. So I pick inverse norm. Because this is written as a less than, I can just type the probability straight in as my area. And then the mean and standard deviation come from the distribution. And I press enter and blammo, there's my value. Everybody's okay? What's different about this problem than the previous one? The inequality symbol is different, right? This is greater than as opposed to less than. Guess what? Inverse norm only works with less thans. So my first order of business is going to be converting this from a greater than inequality into a less than inequality. So to do that, if above A is 20% of the data, how much data is below A? 80%, right? Because there has to be 100% of data total. So I would just convert this to Z is less than A is equal to 0.8. And there we go. So far, so good? What if I have something like this? Oh no! Looks hard, right? Here's the key. What is this distribution? What does the graph look like? It's symmetric, right? So what I can do is split it, and now just go from, I have like that, right? So now I've written it as a strict less than inequality, right? 50% here plus this 21 gives me the 71. That'll give me the x value here. That's going to be my A that I need, right? So you gotta start getting sneaky here on some of these. No, I don't like being sneaky. Should never underestimate the sneakiness. Okay. What have I changed here? Just the type of normal distribution, right? Instead of being standard normal, it's just this other thing. Is that going to change anything that I'm doing? Just have to enter the new numbers for mean and standard deviation, right? But it works. No, nothing tricky there. What if we kind of make this as a story problem, right? Instead of being so helpful in giving you the normal distribution and the probability statement you're trying to solve, what if we take that away and give you a situation where you have to generate that yourself? That's usually the hardest part for students. Cartons of juice are such that their volumes are given by the normal distribution, yada, yada, yada. 5% of cartons are rejected for containing too little juice. Find the minimum volume to the nearest milliliter that a carton must contain if it is to be accepted. So you want P of V less than V is equal to 0.05. Right? So you're inverse norming this because you're looking for the measurement, not from a probability, the observation from the probability. I guess we assumed that the units were milliliters. There's probably more to this question that I just pared down. That sure came from someplace. Sacks of potatoes with means of 5 kilograms are packed by an automatic loader. In a test, it was found that 10% of bags were over 5.2 kilograms. Oh, giving away potatoes. Use this information to find the standard deviation of the potatoes. This is the most challenging type of question you'll run into in this chapter. So, we're looking to find the standard deviation in this normal distribution. The idea here, we're told that P of M is greater, or M greater than 5.2 is equal to 0.10. Normally, we want to just use inverse norm to locate the value to find like this kind of a value. But we don't have the standard deviation, so inverse norm is like out the window, right? So here's what we do. We're going to use a standard normal distribution. Because the percentile, if I do a z-score conversion, should still be 10%. in the normal, standard normal distribution as it is for the original normal distribution. So I know that my z-score is equal to measure observation minus mean divided by standard deviation, right? If I can then find the corresponding z-score, I can plug that in and create an equation, just solve for sigma. Everybody good? Okay. So, to do that, I'm going to solve for z less than z, or I'm sorry, greater than z is equal to 0.10, or switching it, z less than z is equal to 0.9. Remember, this is just my z variable right here, right? I just wrote it in the spot. You could just leave it as z if you wanted to, it's fine. So I go to my calculator, I pull the value for z using inverse norm. I take that value and set it equal to 0.2 over sigma, and then just solve for sigma. My opinion, this is the most difficult type of question we'll ask you to do in this chapter, because it forces you to work fluently between standard normal distribution and normal distribution. It's the only case where like converting something into a standard normal distribution makes sense, given your technology advantages as a student compared to what Mr. Kulik had when he was a student. That's the end of this guy. Next class, we're going to do the chapter 12 quiz. That quiz covers just 12.1 and 12.2. So you should be able to work with a general probability distribution and specifically a binomial distribution. You will have to do binomial distribution stuff with your calculator. So you should be fluent in doing so. My suggestion is things to review. Look at the in-class examples for 12.1 and 12.2. I think provide pretty good examples of like how the questions will be formatted, what types of questions you'd see on your quiz. It's a little guy, it's like a 20-pointer. So it's just like one page front and back. So I don't think it's too big of a deal. After the quiz, we'll do the in-class examples for 12.3. And then next week we'll do the activity and take the chapter 12 test.
Yeah.
Everybody feel okay?
Sounds good.
Okay. Just as a training tip for the in-class activity, we're going to be measuring how long you can hold your breath for. So if you want to start working on your cardio and your lung capacity beforehand to really like crank out some impressive numbers,
Yeah, it's not good.
you know, like I invite you to do so. See if anybody can top 60 seconds.
I can feel 67. What if I pass out?
Well, then the time stops and you pass out, because then you start breathing. Obviously.
You're just looking at it briefly.
I've added links that just like
Does everybody feel good about the schedule, what the plan is, what we've done so far? Today was okay? Again, like, work through, we'll do the in-class examples and you get a chance to work through some stuff. It's mostly calculator, right? The hardest part is knowing what to do from the problem, right? Getting the setup.
Just this
You
weekend.
also got an
No,
email that I
if I
won't be here
have
Friday for a conference.
I'm more
Oh, for the